and John Thompson were talking about yesterday, 30 years ago, that we can study plants from space. And then he went on to create 30 years of Earth observations, the well-known and one and only GIMS data set that everybody uses. And let us welcome him from Turkey, where he's doing some archaeological work, and let us tell us in his own words, how he accomplished that. Take it away, Jim.
Thank you very much, Rama. So I've been asked to talk about how I bundled into using time series data, time series remote sensing data, and that is what I'll try and do. But first, I want to show this really graphic image which Gene Feldman of the CWIS project has produced. It's land normalized difference vegetation index combined with ocean color data from the oceans, where you look at the chlorophyll density. The respective scales for both are on the bottom of the image. It uses CWIS data from 1997 through 2011, and the process you can completely obliterate clouds. So you have a rendition of the average chlorophyll density of the surface of the land and also for the oceans. And for me, it's really cool looking at the oceans, because I know so little about them. Where you have those blue areas of the oceans, you actually have biological deserts. Anyway, so with Earth observations data, we can do all kinds of things. When I give talks to people, and they hear I'm from NASA, sometimes people say, we didn't realize NASA studied the Earth. And so I show this slide, and so within NASA, there are engineers who build instruments, and they fly them into space. Some of them look away from the Earth to study things about astronomy, various aspects of astronomy. The same engineers build phenomenal instruments, look down at the Earth, and that's what all of us use for our science. And with us, highlighted remote sensing, we would be just bumbling along because they provide daily data, weekly data, fantastic data of the atmosphere, the oceans, and the land. And this enables us to treat Earth system science quantitatively. So I have this in just to show that many people are not aware, but a very large percentage of the spectral solar radiance is in the visible region of the spectrum. This is undoubtedly why we see in the visible. This is where most of the energy is. And this is also where photosynthesis occurs. So it's a complex figure. It shows the distribution of energy from the sun, the solar spectral radiance top of the atmosphere. And then it actually propagates through to the surface. Visible portion is delineated with the spectrum blue, green, yellow, and red. Then there's a picture of the atmospheric limb, which Dr. Sellers talked about, which Pierce talked about, this very thin layer of 25, 30, 35 miles of atmosphere on our planet. And then in between those two curves, where we have these black and white areas with respective wavelengths, we have what we call atmospheric windows. So this is just to set the stage that in remote sensing, all of us use satellite data. We look in passive parts of the spectrum where we have reflectance or emitted energy. We also use active devices like lasers and also radar to study the Earth. But it's that we can use all these different wavelengths which enable us to do the wonderful job we're doing. So how did all this start? Well, I kind of bumbled into remote sensing because when I finished my undergraduate degree at Colorado State University in Fort Collins in biology, I couldn't find a job, so I got a job in a bank at Colorado National Bank in Denver, and then later at First National Bank in Albuquerque, New Mexico. But I really hated banking. I just wasn't made for it. And so this drove me back to Fort Collins, Colorado, into graduate school, and I ended up being sort of a walk-on person in a project on the shortgrass prairie of Colorado in the grassland biome of the U.S. International Biological Program, studying primary production. And because I was a biologist, I was in charge of this. I was working with two very clever people, Lee D. Miller, also Pearson, so white shirt. One person hunched over with the longer hair and the horn-rimmed glasses. And I was in charge of clipping, and we were working in a grassland system, so the total biomass production, because it is herbaceous, is what is there. And once you've clipped a few areas, you want to find out better ways of doing it because it's a pain in the neck and it's time consuming and pretty laborious. But we've collected hyperspectral data, and we also then structurally sampled areas that were 1/4 square meter in circular area, like you see here. And it was my job as the biologist in the group to analyze these data. So again, these were hyperspectral data. We had data every 5 nanometers from the near ultraviolet out into the reflected infrared. Here's just one of the figures, and it became readily apparent to me that there is a very high correlation in hyperspectral data between adjacent wavelengths in broad regions of the spectrum and biological or physiological properties of vegetation. So this is a plot where I was looking at R-square values as a function of wavelength between the spectral reflectivity at 5 nanometers versus the lead water content. And the lead water content is a very easy way to tell what portion of the revegetation in the clip is live or dead, because there's very little water or no water in dead vegetation. So this figure shows that you have very high correlations in the red region of the spectrum. The spectrum is on the scale, and also the nearby infrared. And these were 2 wavelength regions where you had different processes, absorption in the red and no absorption in your infrared, which were very close together spectrally. So we decided to build a simple instrument to go out and exploit those on the ground, a simple handheld 2-channel radiometer. At the same time, it's really crucial in any work you do to investigate simulation modeling. And I was in a class on simulation modeling, and I adapted a Markov chain approach to look at spectral reflectance, spectral absorption, and spectral transmission of relief as a function of wavelength, driven by absorption and scattering, 215 wavelengths from near ultraviolet into the water absorption region of the infrared. And by doing this, it confirmed what we were trying to measure. If you could put these quantities into a simulation context, and we would get out what we measure in individual lead. And so it was very important to not only perform field experiments, but to do simulation modeling, and I've benefited a lot from that. Now, it's also really important when you do work to write it and publish it. And I'll make that point here because the 2 people I worked with who were the engineers in the project left the project to work in other areas when I just finished my master's degree. So I was abandoned as sort of an orphan graduate student. And they didn't write up some of their engineering work. So I told them, because I had collected some of the data they used and analyzed some of the data they used to demonstrate their techniques, but I'd be very happy to write this up. I would put myself as the most junior author, just to get the work out in the public domain. And so one of the things I did was I collected some more data with this 2-channel radiometer that I'm holding here and published it in Applied Optics. Well, then people started writing into me. Before we had email, people would write to you, and they would say, why don't you come and bring this 2-channel radiometer? We would like to test it in our locations. By this time, I was a postdoctoral fellow, and I thought, wow, this will be a great way to travel places like Iceland, places in the UK, the south of France, and Sweden. So one summer, I did that. And working in Iceland, this is a photograph of me in Iceland, I discovered that the normalized difference vegetation index was very robust under different illumination conditions. And it dawned on me that maybe this could actually be used in a practical situation. And the data actually held together very, very well. So that's what first dawned on me from field work, that spectral measurements can be very useful under different types of conditions. Excuse me. Then when I got back to the Goddard Space Flight Center, my postdoc, Brent Holman and I decided to do an experiment where we took frequent red and near infrared normalized difference vegetation index measurements of a winter wheat area. This is a picture of when we had our winter wheat biomass and grain harvest. We made these measurements every 4 or 5 days over the growing season. And we found when we summed those that we could explain about 80% of the above ground biomass accumulation. And this is a very narrow range experiment, the same time density, the same microclimate, this is an area of it. The areas which we had in this experiment were in a field were probably 40 by 60 meters, something like that. So then my branch head at the time, Charles Tesler, said, well, look, this is NASA, figure out some way to do this from satellites. So we published this work in 1981. In looking around for the paper we wrote on it, the only possibility to do this was to employ this from the NOAA Advanced Very High Resolution Radiometer, which was going to be launched in an afternoon orbit in early July of 1981, because it had two channels which might be used. But one of the problems initially was these two channels overlapped. Channel 1 not only included the upper part of the visible, but it included part of the near infrared, so it would have been useless. So I went over to NOAA and talked to Stanley Schneider and Dave McGinnis and said, look, there are some very good vegetation reasons to split these two channels so they don't overlap. And for snow reasons, they were interested in doing the same thing, so those two arguments carried the day. And so NOAA then split the channels so that the channel 1 and the channel 2 of the advanced very high resolution radiometers, which are not advanced, so they're not very high resolution, were non-overlapping. And this is what has enabled everything. So then that was done, and so we were sort of waiting on the first NOAA satellite to go up. But in the meantime, a group in northern Senegal, led by Charlie Van Praat, a Belgian friend of mine, was trying to estimate herbaceous biomass in one of the grasslands of the Sahelian region, in the northern part of Senegal, in an area that was several hundred kilometers by several hundred kilometers. So I went over with my handheld radiometer, and I also put in a request to NOAA to get frequent 1 kilometer coverage from NOAA 7, which had just been launched and was turned on for data collection on the 1st of July of 1981. We started a field experiment there. Now, what we were able to do, and I'll show in a second, we were able to confirm that you could do, or you could perform total dry matter accumulation measurements from space. But one of the really cool things about working in Sahelian zone is because you have mountains in the western part of Africa, you have a precipitation gradient that is fairly constant to lines of equal latitude as you go across the continent. And you have a gradient that is about 1 millimeter of precipitation per year per kilometer in the north-south direction. So it's a perfect place to work because you're working along a gradient in this monsoonal system. Now, perhaps some of you aren't familiar with what it looks like in the Sahelian zone. There are marked differences between the rainy season on the right, things are green, and the 9 or 10 month dry season on the left when it's dry. This is the same location. These are pictures taken by Greg Tappan, and it shows this area. There's some background noise here because I'm in the garage. It's right off the sideline. Anyway, so there are marked differences between the rainy season on the right and the dry season on the left. There are even perhaps more pronounced differences between or among years. So 1984, which was one of the years in our experiment working there, turned out to be the driest year of the century. We were just lucky to catch it. Here's a picture of how dry it was in the Sahelian zone. I draw your attention to the fence line on the left-hand side of this image. And then here's the same time of year. This was the 1st of August of 1994, the same time as the previous image, when it's a very wet year. And it's extremely wet. You can see all the herbaceous material. So this is how rapidly things can change. I hope this noise ends soon. Anyway. Okay, so when you do field work, you have all kinds of problems. We became the source of amusement for lots of people. Here were broken down because the car we were driving across the Sahelian zone, the grass in one year or one place was very high, and it blocked the airflow through the radiator, or our car overheated. So all the local people came out from the pumps. From the first series of data, now one of the problems with this set of data is you have to go out and read 1 kilometer data. So we had to try and sample, we get destructively sampled biomass information from areas that were 1 kilometer by 1 kilometer. And to do that, we had to go out with a crew of people at the end of the growing season and sample lots of areas. Well, it was really, really laborious, and we employed a lot of people doing it. But after 3 years, here are all the data we collected from 1 kilometer data on the x-axis, and then the end of season total dry above ground biomass on the y-axis. And we explained 69% or 70% of the variation. So here we confirm that we had measured on the ground with handheld instruments at a meter by meter scale. So then we realized, wow, we can do all kinds of really cool things with ADHR data. And besides, it's all we had at the time. But it also indicated how important time domain is. Spectral domain is important, the spatial domain is important, but the temporal domain is important. It just depends upon what you're looking at. Now I'm going to jump to something more current, and that is some work I've been doing with some coworkers of mine at Alaska. Did about 40 bits on who's the person who has put our data set together. I'm in the lower right-hand corner of this picture. Someone made an avatar from the national web president. And they put a lemur on my shoulder, and they dressed me up in a pure solar spacesuit. And we've also got Epstein from the University of Virginia, and then three of my coworkers from the University of Alaska, Bob Mark Reynolds, Skip Walker, and Bob. And then there's also Joey Camisa, who's one of our CI's people about our space telescope. So we're studying tundra photosynthesis, tundra total granular accumulation. But now, from 1981 to 1982, through the present, we know the temperatures are differentially warming the planet and are more pronounced in terms of anomalies at higher northern latitudes. The left-hand plot from NASA GIST shows the northern latitudes from 1900 through to 2010 or 2011, from 23.6 north up to the North Pole, 90 degrees north. And then on the right-hand side, you have the same data plotted. You notice at the top of it, you have a lot of red colors. That means warmer there. So one of the cool things about tundra is it's very flat, fairly homogeneous, and so it's easy to collect data in areas which are very similar. This is what Skip Walker, who's on the ground right now in the purple shirt, and his team are doing. They're collecting lots of biomass data. Excuse me. So what we have, we don't have many areas where we have biomass data. We have several from North America and several from Eurasia and the molecules. Those data are plotted on the left hand, on the lower left-hand side of the figure. Each of those points represents in blue for North America and red for Eurasia, where we have detailed biomass data destructively collected in a given year, and the coincident satellite data from our GEMS NDVI data set, which is an 8-kilometer data set. And so you notice they hold together very well. So this enables us then to take data where we don't have calibration data, use this relationship, and extrapolate. That's what we do. So from 1982 to 2010, 29 years, we've just added the 30th year of the study. We had overall a 20% increase in the total above ground biomass production in the tundra. 2 papers have been published so far on this. One is Epstein et al., ER et al., and the other is by Mark Reynolds et al., also in 2012 in the Notes and Letters. So if you're interested, these are 2 sources to look at this. But the thing is, we have this rather dramatic 20% increase in tundra biomass production over 30 years. So this is what they would look like. This is a figure which Ranka Manini produced, and it shows several things. In green, we have for all of the Arctic, we're looking at the NPVI and how it has increased from 1982 through 2011. But what you'll notice is the green, the points increased up to 1991 when Mount Pinatubo erupted and cooled the northern hemisphere. The Arctic is limited by temperature, so biomass production and the immediate decrease. As you see, fell off, climate system reset, and then things continued on up to the present. Now, anytime we do any studies, we always compare things to MODIS data and spot vegetation data to make sure different data sets the same result. And so the blue data on the right-hand side of the upper curve for this Arctic area is a direct comparison of MODIS data from exactly the same area, and they agree very well. The slightly lower down on the lower center and right-hand portion of this figure is a histogram of temperature anomalies and our NDVI anomalies from this same area, and you'll notice they agree very well too. It's crucially important to use other types of data to understand what you're looking at. Okay, so we had these interesting trends, this 20% increase in tundra biomass production. Now let's look and see what our sea ice trends have found for looking at Arctic sea ice. Now, Arctic sea ice can be measured very, very accurately because at a wavelength of 1.55 centimeters or a frequency of 19 gigahertz, there's a marked spectral emissivity difference between sea ice, which has a spectral emissivity of 0.8 to 1, and ocean liquid water, which has a spectral emissivity at that wavelength of about 0.4. So it is really, really easy to measure and distinguish sea ice from ocean water. Now, I show this because I like to tease graduate students and undergraduate students. This is how we put how the sea ice people put our graduate students and undergraduate students to work. And I think by doing this work, just like my work with flipping, makes you realize there are better ways of doing it. This is kind of a gag photograph. Anyway, so the sea ice data show, just like our Arctic tundra data showed this increase over time, the Arctic sea ice data, here we're looking at the yearly minima in the Arctic sea ice extent. And you'll see it has the opposite slope because temperature is affecting both. In the case of Arctic sea ice, it's melting it. In the case of the tundra vegetation, it's warmer, so it's growing more. So once again, in remote sensing now, we have a lot of different data types we can look at, see, we can look at one phenomena with one, a different phenomena with some other types of data, and then compare them. Now, I give a lot of talks about climate. Now, unfortunately, the local mosque is now coming on with their call to prayer, and I'm not sure if you can hear it in the background.
Yeah.
So, whenever that happens, it's FS filter time. About sea ice, some are say, well, sea ice, you all who talk about the Arctic all the time, what about the Antarctic? Because sea ice there is increasing. And these are the Antarctic sea ice minimum data, which occurred at the end of the austral summer in February, which is the minimum. And you'll notice there is a trend over time which is increasing. So what the hell is going on? Well, there are marked differences between the Arctic and the Antarctic. The Arctic is an ocean surrounded by land for the most part, and the Antarctic is a continent surrounded by ocean. So they're very, very different. So how can we resolve this difference? Well, let's look at the gravity data. These are new data which are revolutionizing our understanding of ice sheets, aquifers, and so I'm going to show some gravity data from the Gravity, Recovery, and Climate Experiment. This is an experimental German NASA mission. It has a baseline of 220 kilometers, 2 satellites from the same orbit with very, very accurate ranging between them to plus or minus 1/1000th of a millimeter. And so what you measure is variations in mass on the surface as these two satellites come along. When one satellite comes upon an increase in mass, it will speed up, relative to what's happened before. The distance between them will increase, or if there's been a mass loss, then there will be just the opposite will happen. So from these data, and the distances between these satellites at a 220 kilometer spacing, you can see what is happening, the variations in mass and mass units directly at the surface. So you can use these data to study what's happening to ice sheets, and in particular, I want to compare what's happening to Greenland and what's happening to Antarctica in terms of mass variations. On the left-hand side this figure from Scott Lutke and Dave Goldman's Goddard Space Flight Center. You see a mass loss in Greenland during the summer, a mass increase in the winter, mass loss in the next summer, so on like this. So over these 800 years of GRACE data, from Greenland you have about a 1,200 mass loss. That's about 1,500 cubic kilometers, or 10 cubic miles. And that by itself has contributed 3.4 millimeters to global sea level rise. But let's look at Antarctica, too. Here's a figure which looks, the top curve in blue is Greenland, the middle curve is from Antarctica, and the lower curve is from the Gulf of Alaska. So in all cases, you see that Greenland is losing ice mass, and so is Antarctica. So all of this nonsense about, well, the Antarctic sea ice show that Antarctica is getting colder. No, Antarctica is getting warmer, and it's losing mass, and it's losing mass, and accelerating with. You can see here. It gains mass in the austral winter, loses mass in the austral summer, but the curve is clearly, the curve derivative is clearly negative. You also see below them what's happening in the Gulf of Alaska, where you also have mass loss. So here we started off looking at photosynthesis in the tundra. We got one result. Then we looked at the sea ice data, which agreed with what we saw there. But then people said, well, what about the Antarctic sea ice? So now we go to gravity data, and now we bring conformity and see that synchronous warming is happening to our planet in terms of ice in all these locations. Now, it's always good to show our humanist friends that we in science are also interested in poetry. And this is a poem about nature's best thermometer from Henry Pollack. He's written a very interesting book called The World Without Ice, about the cryosphere. Because nature's best thermometer is probably ice. Because the Earth warms, ice is going to melt. If the Earth cools, we'll have an expansion of ice. So ice asks no questions, presents no arguments, reads no newspapers, listens to no debates. It is not burdened by ideology. It carries no political baggage. It changes from solid to liquid. It just melts. So I use this in all of my global warming talk. Now, here's a figure which I just received several hours ago from Ray Manini and his group, taking our new data set, which we're now starting to beta test, which runs from July of 1981 through December of 2011. Jorge Pinzon is the person who put this data set together and calibrated for them. And now we're able to look at 30 years of global satellite data, albeit at an 8-kilometer spatial resolution, and start to see how things are changing. But again, anytime we use these data that are presently being beta tested, you have to compare them to MODIS data for the corresponding periods. So this is one example of how my work, which started off, I was trying to escape from working in a bank, and then in a graduate program using hyperspectral data, which then moved into the time domain, and then jumped to satellite data. In the process, I've had the opportunity to work with a lot of very clever friends and colleagues. There's a lot of work to be done, and it's very important to continue this work. 30 years of data are great, 40 years would be better. Now, it's important because all the data sets I shown are really useful to address climate, and of course climate is determined by the global energy balance. And photosynthesis and carbon cycle are very important. I personally feel through cosmic good fortune, the Earth has retained water in the liquid phase for billions of years. We're just damn lucky that we have a planet of a certain mass, a certain distance from a certain type of star or sun. But climate sensitivity can be forced very easily one way or the other. And so this is why we have to be very careful about our use of fossil fuels. So when I teach at the University of Maryland, although I haven't taught in several years, I try and sort of do different things. And I came across what I call the remote sensing creed, that I want to understand life on our planet. I don't want to be limited by our eyes or our sensory system that's optimized for a 5880 Kelvin star 93 million miles away. So therefore, I have to use the electromagnetic spectrum. This is what we do in remote sensing. And there's a lot of fun, there's a lot of work to be done. There are many pressing or science questions for students to work on. And I'll be happy to answer any questions.
Thank you, Jim. Any questions? Yeah. Okay.
Hi. I did have one question with regards to the slide you were showing with the Antarctic sea ice, the subtle increasing trend there in your graph. I couldn't help but notice too that the variability was increasing pretty drastically as time went on. Do you have any thoughts on what's driving that?
No, I don't. It is directly related to ocean circulation in the Southern Ocean. I could make the argument that the trend is overwhelmed by the variation, so it's not something I would bet on. If you look at the slope, 2.6% per decade, plus or minus 4.4%. So you can actually say, statistically, this is inconclusive and we need more data, and that's what I think. It's just a very noisy system because of the interaction of the Southern Ocean with the ice sheets.
I totally agree. Thank you.
You're welcome.
Anybody else? Okay.
What are you doing in Turkey?
Well, what I'm doing in Turkey, I'm going to turn this up slightly, maybe you can see that, or you can't. What I'm doing, NASA has a program in space archaeology. And you're not studying the archaeology of things from outer space or the Apollo program, things like that. But you're taking NASA tools and techniques and data and applying them to archaeology. And so I'm at the site of Gordian in central Anatolia, in central Turkey, and we're performing geophysical surveys of areas. We've also reconstructed using the Landsat data in the past 40 years, the land use history around the site of Gordian. Gordian is the site where Alexander the Great in 333 BC cut the Gordian knot with his sword. It was this knot which no one could untie, and the legend associated with it was the person who could untie the Gordian knot would become the ruler of Asia. So Alexander comes here with the Macedonians in 353 BC. They were fighting against the Persians. They come to Gordian. The town didn't resist, so he came peaceably. And when they showed him the knot, he said, "This is no problem." He had a very sharp Macedonian sword. So he just whacked it with his sword and cut the Gordian knot, and then became the ruler of Asia, at least for a while. So I'm here as part of the University of Pennsylvania team doing geophysical surveys.
Hi, Jim. This is Jennifer Dungan. We have a question from your friend Jean-Paul Malingro, who's joined us on the internet. He says most significant land cover changes are taking place in agriculture and tropical forests. Can you say a word on your work in those areas?
Yes. Well, right now, especially the tropical seasonal and tropical dry forests seem to be being converted to agriculture at a very rapid rate, principally for biofuels. I think that's driving a lot of oil palm, for example. And with satellite data, we can follow this year to year. And it's extremely important for us to conserve tropical forests for two reasons. One is climate, because of all the carbon they contain, but it's equally as crucial because of biological diversity of all the species that live there. So fortunately, there are some people who have taken what Jean and I have worked on before on tropical forests, and very current, people like Matt Hansen and others, that with satellite data now we can follow this globally year by year and bring pressure to bear on areas where clearance is illegal or is prohibited. But it's one of the many uses of satellite data, and this work is vitally important.
Other questions in the room?
I see a question from Rango.
Yep.
Which says, Jim, looking back, you sometimes wonder how your EBI data has morphed into a whole new field of science. Well, yes, Rango, I feel that I feel similar to the story you hear about someone who's asleep on the turnip wagon in the Middle Ages as you're going through a village and hit a bump and you fall off and you end up in a really nice village. Yeah, it surprised me. I never thought something like this would happen. I was just really curious to see if you could use AVHR data, and then we had to figure out how to recalibrate the data. Of course, you can do things much better from MODIS, but with MODIS you only have 10 or 11 years versus 30 years of data from the same instruments, from clones of the same instrument.
There's a problem.
And it's,
I think he's just typing away.
it's always disconcerting in some ways, but encouraging in others. To see students coming along, retrain, just leapfrog over you, and then go on to do better and better things with the data. So once again, it's been a pleasure to work with this data, to provide it to other people, and we will be releasing this set to everyone probably in about 6 months after we find many of the problems associated with it.
So, Jim, are there any plans to continue the AVHR sensors themselves into the future?
Well, we think we may get 5 more years out of it because NOAA transferred its last 3 AVHRs to UMITSAT for their MEDOPS polar orbit meteorological sensors. And they're providing global 1 kilometer data now. It's unfortunate that NOAA didn't do this, but MEDOPS people are providing global 1 kilometer data right now. So we think they will get for the next 4 or 5 years, and hopefully 5 years from now we'll have a 35-year or so from the same instrument.
Someone in the chat room asks how do trends in AVHRR compare with trends in MODIS over other biomes, especially more heterogeneous ones such as mixed forests?
Well, that's a good question because you're comparing, well, we don't know, but that's what we're looking at right now. And so if you perform these analyses and you perform them, taking into account spatial differences, differences in spatial resolution, and the techniques you have to use to compare apples to apples, I suspect they will be the same. I'll be extremely surprised if they're not the same. But you have to perform those tests correctly. For example, the uncertainty in terms of geolocation of our data are plus or minus 1 pixel. So we're talking about 8 kilometer data. That's something on the order of 24 by 24 kilometers. So you would need to make that comparison at that scale with MODIS data to be sure you're comparing the same areas on the ground.
I have a question. If we can go back on the slides to the global
Sure.
NDVI average.
Okay. Yeah, that looks really interesting. I'm going the wrong way. Hold on 1 second.
The 30-year average data set.
Yeah, I was trying to find it. Maybe it's further back. Let me go forward. Was that toward?
There.
Sorry about that.
Jim, I was wondering, I was always peering over these average images of average NDVI because there is so much information here, and we've been looking at these figures for years now. And last night, when I was looking at this figure, I see here in Oceania, you see the tip of Australia, and above it, I think it's Papua New Guinea, maybe. Mm-hmm. And it's amazing how spatially close they are, but in Papua New Guinea, it's tropical forest, and just maybe a few 100 kilometers south in Australia, it's less green. I was puzzled about it.
Well, that's always puzzled me too, Rango. But in Australia, where you have your tropical forest, it's only on the extreme eastern part of the country, and actually in the northeastern part of Australia on the coast. But yes, that is very curious. It's also really interesting for me. I was studying this, and when we started making these measurements, or when we started producing images like this from 1 or 2 years of data, there were a lot of people who told me that I was completely stupid for trying to use 1 and 4 kilometer data to study anything about the land surface, including some very good ecologists who I won't mention their names, but we're really silly. But I think when you see an image like this, and when you can look at areas, immediately many questions like you have just elucidated, expressed frankly, come to mind, and you can focus your attention on, well, let's look at these areas. What are the reasons for this? How do the climate data look for these regions? What are the differences? What is the atmospheric circulation? And all kinds of other information is brought to bear to see what's the reason for this. But I've come to believe very strongly in the accuracy of the vast majority of the more recent data. And instead of thinking, well, maybe we did something wrong, instead think, let's look very carefully by them, because it looks really, really interesting.
I agree.
So Mao Sheng asks, what cautions should we take when using NDVI? What do you think the limitations are?
Well, okay. Thank you, Mao Sheng, for asking this, because I get extremely irritated. People say, well, the NDVI saturates. We know that the NDVI is directly related to the absorption of FR by plant canopies. So, and the reason that it asymptotes is because there is no more absorption, because all of the visible flux, for the most part, say 95, 96% of it, has been absorbed by green leaves. So it actually reports very accurately what's happening in the canopy. If you want to use another index, like the so-called enhanced vegetation index, then you take the terms and you multiply them so you weight them more heavily, but then you no longer have an index which is related to APAR. You have an index which is more heavily related to the density of green leaves, perhaps LAI or something like this. So my caution would be, if you're using NDVI data, realize first and foremost that they are related to APAR, to energy absorption, as many studies have shown, and don't try and use them for something else.
Jim, over the years, I'm sure you have seen hundreds of papers written using your data set. Do you have any study in mind that took you completely by surprise? Oh.
That's a good question. I'm sure there were. People have done some very clever things with it. I don't like Sarah Palin. I can't think of what the papers were, even though I've read them.
Marta asks, could ND... Oh, I'm not.
I still think.
No, actually, well, there have been several papers where the creativity of people to use NDVI data in ways has really surprised me and also encouraged me. But there have been several, especially in some of the areas where NDVI data have been linked or have been used to drive atmospheric models and represent land surface conditions. That's one area where I'm very encouraged and was very surprised. Although when you think about it, it seems very logical. Now, I see also, March has asked a question, but NDVI changes because the leaf water content changes. Yes, you can use NDVI data to study droughts, and of course in a drought you have less water available for leaves because you then lose your chlorophyll density in the areas which are water limited. And so that's one way where NDVI data reflect drought conditions.
There is a fascinating article by Hans Tomowick and others very recently in Nature Climate Change, where they used NDVI data to monitor the population of lemmings. And lemmings are small rodents with a big temperament. And in some years, they lay waste to so much vegetation that the devastation can be seen from space. So this paper came out in Nature Climate Change by our colleagues in Fennoscandia, Hans Tomawick, Terry Callahan, Johan Olofsson, and others. So that is surprising.
Yeah.
And that's great.
It's wonderful.
Yes, I would agree, Rango. It's very surprising, and I'll have to read it, but it seems like a very interesting use of NDVI data.
That they can be monitored from space.
Yeah. Yeah, there is something similar in the Yellowstone where
Yes.
the bisons actually graze so they actually stand in a row, so they actually in the graze, from day to day. You can see they change in NDVI.
Oh, wonderful.
Yeah.
Cross.
It's like a lawnmower, It's just,
I think yes, a very big lawnmower. But one of the things, to answer your question, Rama, I was very surprised to read that the USDA had brought up insurance, excuse me, and it was based on NDVI data. And it's run out of using data from the USDA Center. But when I saw that NDVI data will be used in some insurance sense or purpose, I was extremely surprised by that.
yeah. Okay.
Jean, there's another question that popped up about NDVI as a proxy of tree fraction, leaf area, and roughness. And do you have any cautions about that?
That's something which I'm not knowledgeable about. It's too bad that Pierce Sellers is not here, because he can certainly talk about that in detail. Anytime you use data, you have to be careful that what you're doing is appropriate for data. And I've never thought about roughness, and especially tree roughness, with respect to vegetation indices. So I'm completely ignorant and understand that.
Okay. Well, with that, we'd really like to thank you, Jim, for joining us all the way from Turkey. It's been a real pleasure.
You're welcome.